Now, today we are discuss about normal subgroup. A subgroup capital H of a group capital G is said to be a normal subgroup of capital G. If X H X inverse for all X belongs to G and for all small h belongs to capital H. If X H X inverse belongs to capital H, then capital H is called normal subgroup. It is denoted by H is a normal subgroup of capital G. Note point. X H X inverse, it contains all the elements X H X inverse. So H is a normal subgroup of capital G if and only if X H X inverse subset R equals to capital G for all X belongs to G and small h belongs to capital H. So theorem, it is the important. A subgroup capital H of a group capital G is normal if and only if X H X inverse capital H for all X belongs to G. Proof. A subgroup capital H of a group capital G. This is the common one. This is the common point of the necessary and sufficient part. Necessary part. What we have to consider? Capital H is a normal subgroup of capital G. What we have to show that? X H X inverse is equals to capital H for all X belongs to G. Since capital H is a normal subgroup of capital G, by the note point, what we have to write? X H X inverse subset R equals to capital H for all X belongs to G and small h belongs to capital H. So G is a group. It satisfies associative identity inverse. By the inverse property, every element of capital G has its own inverse. So X belongs to G, X inverse belongs to G. So by 1, we have to substitute X is equals to X inverse. X inverse H, X inverse whole inverse subset R equals to capital H. X inverse H, X inverse whole inverse is equals to small x subset R equals to capital H. So now we have to pre and post multiplying. Pre multiplying with the small x, post multiplying with the X inverse. So x into X inverse H X X inverse subset R equals to X H X inverse. X into X inverse is equals to small e H e subset R equals to X H X inverse. So H, we know that HE and EH is equals to capital H only. Subset R equals to X H X inverse. From 192 A subset R equals to B, B subset R equals to A. From 192 we have to write X H X inverse is equals to capital H. This is the necessary part. Next we go to the sufficient part. What we have to consider? X H X inverse is equals to capital H. What we have to prove that? Capital H is a normal subgroup of capital G. By the definition, what we have to prove that? Capital H is a normal subgroup X H X inverse capital H for all X belongs to G and for all small h belongs to capital H. For take two elements, for X belongs to G and H belongs to capital H. X H X inverse belongs to X H X inverse by the coset. What is the coset definition? AH is equals to AH where H belongs to capital H. Same as X H X inverse. It contains all the elements X H X inverse for X belongs to G and H belongs to capital H. So X H X inverse belongs to X capital H X inverse is equals to capital H because what is the consideration? X H X inverse is equals to capital H. So X H X inverse belongs to capital H. This shows that this is a normal. Capital H is a normal subgroup of capital G. Next go to the another theorem. Very important one. Every subgroup of an abelian group is normal. So proof, let G be an abelian group, H be a subgroup of capital G. What we have to prove that? Every subgroup of an abelian group is normal. Every subgroup, here capital H is a subgroup, capital G is an abelian group. H is a normal subgroup of capital G. It is enough to prove that by the definition of the normal subgroup, X H X inverse belongs to capital H. For all X belongs to G and for all small h belongs to capital H. So let small h belongs to capital H, small x belongs to G. And E is the identity in capital G because G is a group, it satisfies associative identity inverse property. So by the identity property is the identity in capital G. H can be written as H is equals to E into H. E can be written as E X into X inverse into H by the associative property. X into X inverse into H. X. Here already given G is an abelian. Abelian means AB is equals to BA. X inverse H is equals to H into X inverse. H is equals to X H X inverse. Nothing but H belongs to capital H. H is equals to X H X inverse belongs to capital H. By the definition of the normal subgroup, H is normal subgroup of capital G. Example, capital G is equals to, we know that capital G is equals to 1 minus 1 I minus I is a group with respect to dot. We know that take any subgroup of capital G, H is equals to, I am taking here capital H is equals to 1 comma minus 1 is one of the subgroup of capital G. By the above theorem statement, every subgroup of an abelian group is normal. Here G is an abelian, H is a subgroup, so H is a normal subgroup. H is normal subgroup of capital G. Let us go to the important theorem. A subgroup capital H of a group capital G is normal subgroup of capital G if and only if each left coset of H in G is right coset of H in G. Proof. A subgroup capital H of a group G. What is the necessary part? Capital H is a normal subgroup of capital G. What we have to prove that each left coset of H in G is a right coset of H in G. So since capital H is a normal subgroup of capital G, what is the previous theorem? X, capital H is a normal subgroup of capital G. X H X inverse is equals to capital H. So X H X inverse is equals to capital H. So post multiplying with the small x, X H X inverse of X is equals to Hx. By the associative property, X H X inverse into X is equals to Hx. X inverse into X is equals to small e. Capital G is an abelian group by the capital G is a group by the identity property and inverse property. X H E is equals to Hx. We know that H E is equals to H. X H is equals to Hx. Nothing but every left coset of H in G is a right coset of H in G. Again, sufficient part. Consider every left coset of H in G is a right coset of H in G. What we have to prove that H is a normal subgroup of capital G. Every left coset of H in G is a right coset of H in G. Here XH is equals to HY for some Y belongs to G. We have X belongs to XH by the coset definition. XH is equals to HY. So clearly X belongs to HY. By the coset property A belongs to HB, HA is equals to HB. So HX is equals to, in place of A here small x, in place of Y here B, A belongs to HB is equals to HA is equals to HB. Hx is equals to Hy. Hx is equals to Hy is equals to XH. So LHS is equals to RHS. XH is equals to HX. Both sides multiplying with the X inverse. Post multiplying with the X inverse. So XH X inverse is equals to HE. XH X inverse is equals to capital H. By the previous theorem, whenever XH X inverse is equals to capital H, H is a normal subgroup of capital G. Another theorem, a subgroup of capital H of a group capital G is normal subgroup of capital G if and only if the product of two left or right cosets of H in G is again a left or right or left cosets of H in G. Here we have to prove that H is a, consider H is a normal subgroup of capital G. We have to prove that it is the product of two left or right cosets of H in G is again a right coset of H in G. By the previous theorem, what is the previous theorem? Left coset of H in G is equals to right coset of H in G. XH is equals to HX. Similarly, here we have to take HA is equals to AH. So take three right cosets HA, HB, HAB. HA into HB, H of, by the associative property AH of B. H of AH is equals to HA. So H of HA of B by the again associative property HH of AB, HAB. We know that HH is equals to H. This is also one of the theorem of the coset. Sufficient part. Consider every left or right cosets of H in G is again a right or left coset of H in G. Take 2 right, again a right coset. So taking HA into HB is equals to HAB. What we have to prove that H is a normal subgroup. For small h belongs to capital H and x belongs to G. X, H, X inverse. Any element multiplying with identity, we get same element E, X, H, X inverse. E into X is equals to X only. So, by the definition of the coset, EX belongs to capital H into X, H into X inverse belongs to H into X inverse. So, clearly X, what is the left side? X, H, X inverse belongs to H into every left. The product of the any two left cosets is again a left coset, or the product of the any two right cosets is again a right coset. H into X inverse is equals to small e, nothing but identity. X, H, X inverse belongs to capital H. For all x belongs to G and small h belongs to capital H. This shows that capital H is a normal subgroup of capital G.